Welcome back, everybody, to this week of Physics 4411. I just wanted to give you some quick messages before we move on. Just to quickly remind you, the GitHub address, which is something I put in the chat here, is the one you will see here, and in the chat. And the lecture material for this week is also put in the chat here. You can also fetch this down as a Jupyter notebook. I also wanted to remind you quickly, in case you may have forgotten about this, if you go to the University of Oslo official website for Physics 4411, in case you are not familiar with that, the university has a service here like this schedule. If you click on that one for the semester, and then you look at the, for instance, the lecture plan here, you can actually subscribe to these activities, which means that you will get a message, either a text or an email, when there are changes. And I will typically place the link to the lecture material, like for this week, of February the 16th, you will find the link to the Jupyter notebook, which I'm going to use today. And then after the lecture, I will link up the video of the lecture and also the whiteboard notes. So you should then have access to all the material. So this website of the University of Oslo with the schedule has the possibility to allow you to subscribe to updates, continuous updates here. And then I will also place messages typically every week about the plans for the week. And I have to apologize because I think I forgot to send an email to all of you. I will try to remember that next time. Okay, so feel free also if you have questions about practicalities and other things, just shoot me a message. Alternatively, you can also today, during the lecture here, you can put a question in the chat or message in the chat or just unmute yourself. So what I wanted to, unless there are any questions, the topic today is about the finalization of importance sampling. And if we get time, we will start with the gradient methods and the optimization part. So the plan, more or less, is to finalize this discussion on importance sampling with computational aspects. And then we are going to, if we get time, we are going to look more into the theory of this Fokker-Planck and Langevin equations. And then we have the so-called gradient descent methods. If we get time, we will get into that topic there, which is going to keep us busy the next week and the week thereafter, because this plays a very important role when it comes to the optimization part of the variational parameters. So just to anticipate the discussion which is going to come when we're going to deal with gradient and optimization methods. So many of you have met these methods in courses on machine learning, where optimization plays a central role. Now here, as you've probably seen, we are calculating the energy as a function of variational parameters. So what we are doing now is to optimize an integral as a function of these parameters alpha, as we call them. And we are looking after the minimum of the energy. The energy is normally, and most of the cases which we are going to encounter in quantum mechanics, is a convex function. So we are looking after a minimum, and preferentially a global minimum, which is typically the ground state of the system. Now, in this search, till now, we have simply done what we might call a not very intelligent and brute force way, where we compute these variational parameters and the energy expectation value by just running a given number of Monte Carlo cycles for every parameter alpha, and then by the eye, we are searching for the minimum. Now, this is not the most efficient way of doing that. And there are methods which will allow us to, with fewer Monte Carlo cycles, to find the optimal parameters around the minimum. And when we have these parameters, that's when we can start and unleash the big Monte Carlo calculation, where we actually collect statistics for calculations of the ground state or the lowest lying state with a given symmetry for a specific Hamiltonian. So this is the the kind of things which are to come. And it's going to involve some more complicated calculations in the sense that we have to calculate the derivative of the expectation of value of the energy as a function of these variational parameters. Now, before we move on, I wanted to remind you a little bit about this important sampling feature, which is now a way to guide the random walkers in this space of possible configurations where the particles can be. And then with this kind of guidance, we can then hopefully have a more efficient sampling of positions in space, which contribute to the expectation value of the energy or any other type of operator. So let's take a look back at the Jupyter notebook here and the material which we went through last week. So the Fokker-Planck equation, and this is something which at the end of the slides here, you will find a derivation of the Fokker-Planck equation, and it has its roots in transport theory and statistical mechanics. Unfortunately, some of these technicalities and the basic theory are things which we will not have the time to cover. But if you wish to read more, there are links in the slides here at the end, which you might find of use, or you may actually look up textbooks which are linked down in the text here. So the basics of the Fokker-Planck equation, if you wish to just keep this at an overarching level, is that if we have a probability density, which in our case is the wave function squared divided by its norm, then we can change the diffusion equation. And as we discussed last time, the diffusion equation can be derived from a Markov chain. And then we would add to this a kind of drift term. And then this is accompanied by an equation which is called the Langevin equation. And this equation is then used to find the new positions given this drift term. Actually, this equation here is a kind of equation which is based on Newton's equation of motion, and where you have a random force which gives rise to fluctuations. So you have a long distance force which takes care of the long-term correlations in the system and forces. And then you can have some short-term fluctuations which are added, and they are normally simulated as a kind of normally distributed force. And the without us having gone into the full details of the integration of this equation, you can solve this as a stochastic differential equation. And then you have the new position, which we need to implement, where we have x plus this parameter, which is in front of the Schrödinger equation, which is just minus h squared divided by 2 times the mass. And we normally put these parameters equal to 1 when we are scaling the equations. So this d is just equal to a half. And then we have the quantum force. There is a time step delta t. So this becomes a parameter. And then we have a Gaussian random variable, which we have to draw. And then this is multiplied by the square root of delta t. So if you go into textbooks about solving stochastic differential equations, you will actually find this solution here when you have a normal distribution for. So this eta is also assumed to be normally distributed. So this is just some kind of noise which represents short-term fluctuations in a setup of a Newtonian mechanics problem. So there's a lot of classical mechanics which enters here together with what's normally called classical statistical mechanics and classical diffusion theory. So in the equations which we have looked at here, there is no quantum mechanics. So in just a few moments, I'm going to bring in the link to quantum mechanics. Now, the thing which we then end up having to do is to compute this so-called quantum force, which in our case, in order to satisfy the steady state equation, that means that when the probability which we have becomes stationary means it's time independent. So it means in turn that you will just fluctuate around the expectation value for, let's say, the energy or any other type of expectation values. And then the steady state equations put a requirement on this term f, which in our case, due to the form of the probability distribution, which is the wave function squared, this has to be given by the gradient of the wave function divided by the wave function. And this is something which is loosely in the literature called for the quantum force. And that term is something you can think of being responsible for pushing the random walker towards regions of configuration space where the trial function is actually larger. And larger trial wave function means also larger probability, because the probability is proportional with the wave function squared. So from practical terms, it means that this quantity here, which is often called the Green's function, or probability of jumping from x to y in a time step delta t, is something which we can compute analytically. And that allows us to modify the metropolis test and bring in a condition on the transition probability multiplied with an acceptance probability. So the acceptance now for making a move is then governed by this ratio Q, which now contains the Green's function, which represents the probability here of jumping from y to x, and then going back again from y to x. Now, before we move on, I wanted to say something about the link between what you see here and quantum mechanics. And this is something which not all of you may have seen. And when you go through these links, you may perhaps appreciate a little bit better the kind of connections which we are doing and why we are trying to simulate these equations using inputs from classical transport theory and not quantum mechanics. Well, there is some quantum mechanics here in the sense that we have a wave function squared. So the thing I wanted to just briefly mention here is the link with quantum mechanics. And then after that, we are going back to the whiteboard and we're going to look at technicalities which we need to think of when we are setting up our code. Now, the problem which we have at hand in project one, in the beginning, when we don't include interactions between particles, is actually a pretty straightforward one given by the harmonic oscillator. And there we have analytical equations in all dimensions, and that makes it much easier to develop a code and benchmark every ingredient which we are adding to the code. But let me try to make a link with quantum mechanics here so that you can see that. So let's just try that. So I assume that not everybody, so there are many concepts here which link to things you may have seen in different physics courses and mathematics courses. But my guess is that many of you may not be too familiar with this. But let's now just remind ourselves about the continuous Markov chain, the way we wrote it last time. So normally when you see this derivations, you will see a discretized version of it, but you obviously can assume that the probability function is a continuous function, and same happens with the transition probability. So let's just write continuous Markov chain, and what we have is a probability Wi of being in a position y. So y here could be a position, or it could just be an abstract quantum mechanical state. So we don't need to specify it here. So think of y, you can think of that as a random walker, which has a probability of being in a position y at a time t plus delta t. So we make a move, and this is now given by an integral. So this is the continuous version of the Markov chain. And these x's, which we have here, they are drawn from the domain of events, which are possible by the probability distribution. So w, lowercase w, is a probability distribution of being in a position y or state y at a time t. Now, this is now given by this uppercase w, which is a transition probability. And this is normally written like a probability of making a transition to a state y at the time delta t. plus t, given an initial position x and y here. It doesn't need to be an initial position again, it could be an initial state of the system, where x represents given quantum numbers and positions. And this is then multiplied with this wx, the probability of being in a position or state x at a time t, and this is integrated over d of x here. So this is a continuous Markov chain, and when we are just looking at the plane diffusion problem, since Markov chains are intimately linked with diffusion, we can actually solve this equation here. We can find the so-called solution to the differential equation for both the probability W and the transition probability uppercase letter W. So the question now is, how do these link with quantum mechanics? Does this equation here link with quantum mechanics? And I'm just using the acronym QM for quantum mechanics. Now, let's now assume that we have a Hamiltonian operator, H, and I'm trying to be consistent with putting hats on top of operators, but I may forget it in the equations below here. So if I forget it, please forgive me here. And this state phi 0 is an eigenstate of this operator, and it has an eigenvalue E0 multiplied with this phi 0 here. Now, a Hamiltonian operator is Hermitian. It is a normal operator, which means that H times it commutes with its self-adjoint. Also, being a Hermitian operator, it has to obey the properties of unitarity. So which means that we also have that H, we assume that this is obeyed now. So its inverse is now equal to H minus of H. And we know that the inverse is actually equal to the self-adjoint of that operator. And this is given by the unity matrix. If we now are thinking of this as a finite dimensional matrix, H. So we're just putting the hats on top of here. Now, that means that if I look at the expressions for H, so we're assuming now that the inverse exists. That's a very important thing. And if you think of H in terms of a linear algebra problem, what you know then is that you can rewrite this equation, which we have for the eigenvalues, in terms of a standard linear algebra eigenvalue problem. And then we would have to diagonalize a matrix. And diagonalizing that matrix, we also assume that the inverse of that matrix does exist. So you can think of this very much along standard linear algebra methods, which you have encountered before. So if I take the inverse of this operator, which is the self-adjoint, just keep in mind that H minus is equal to H, the self-adjoint of the Hermitian matrix H. So we are assuming that this is an Hermitian operator, it is diagonalizable, and it has an inverse, and it's a normal operator. So these are all the kind of conditions which we put, or constraints which we put on a Hermitian operator. Now, the operation here on phi 0, if we look at this one, is something which we can rewrite in terms of E0, and then we have the inverse multiplied with phi 0 here. Now, if now H, as we know it, is a differential operator, and this is something we can quickly see if we think of just the harmonic oscillator. Just think of this as a one particle or single particle harmonic oscillator operator, or just a standard Hamiltonian for a single particle. Then we know that H would now contain the kinetic energy divided by 2m, and then there is some kind of potential or external potential which the particles move in. And when we see this a differential operator, this is simply because we have the second derivative which is involved here. And normally the potential may contain operators, but in many cases just contains a scalar. So you can assume that the potential in most cases is just given by a scalar. So the essential operator is actually a differential operator. So when this is a differential operator, we know that the inverse then must be the opposite of differentiation. So that means that this inverse operator is actually an integral operator. And you can see that quickly now when we now look at the equation here. So it means that this is an integral operator. If we now look at the action of this operator here, H inverse, and we go back to the equations which we had here. So if we now look more carefully at this one, what we can do now is in here, we can insert a completeness relation. So we are going to take this term here and simply insert a completeness relation. And we know that this expression here, since this is the identity here, it's equal to phi 0. So let's now rewrite the equations by inserting a completeness relation. So we have an integral over x, and now I'm not setting up the domain. I'm just assuming that I'm performing an integral over d of x for the relevant domain. And then I have now, and this could be typically from minus infinity to plus infinity. And then I have my x, d of x, dx here. And when I insert that one into that equation and multiply from the left, and multiply from the left, with the state y, what we get then is the following. So we get a new expression. So we have y of phi 0. And this is something which I will rewrite as the state phi of y. So this is a kind of normal definition which you have in quantum mechanics. And this is now given by this E0, which we have here. So we have this phi 0. And then we have an integral from minus infinity to plus infinity. And then I have my y. And then I have the inverse operator, y, h inverse. And then I have x. And this is multiplied with x of phi 0. And then d of x. And then I would simply rewrite the last term here as a phi 0 of x. This is just another way of writing the definition of that one. Now, the quantity which you see in here now, this specific quantity, is normally called either the Green's function or the propagator. And for those of you who may have taken a course in mathematical physics, you may have seen the link between differential equations and Green's functions and operators. So this is also called a propagator. So if somebody here has taken a course in quantum field theory, you may recognize these quantities, or if you've taken a course in many-body physics. So this is a propagator, or just the Green's function. And it leads to the theory of Green's function. And this is often written in the following way: a g of y, and then x. And that's given by a y of this inverse operator of x. Now, this quantity represents, if you think of it now, the way we have written things, it represents a transition probability. So this represents actually a probability of making a transition from a state x, of making a transition from, and here we have not plugged in time, but we could also plug in time if we wanted, from x to the new state y here. So this is something which clearly starts mimicking what we have seen with the Green's functions, now with the transition probabilities, where we now can interpret this Green's function as a probability of making a transition from a specific state X to a specific state Y, and vice versa. So if you now look at this differential equation which we put up, this state phi of Y, we can actually rewrite this one in terms of, if we now just take out the E0 term, so we have a Y multiplied with, so this is H, which now depends on Y, of the H minus, and then phi 0 of Y. And this is something which we can rewrite as an integral from minus infinity to plus infinity. And then we have H of Y multiplied with this G of Y of X and multiplied with phi 0. So it's not so difficult to actually see how we can transform into that equation. Now, the thing which we have here is that the Green's function is just a rewrite of the original problem, which we had up here. So if you now think of the original problem, which is here, written out in terms of a differential operator, or which we could rewrite in terms of a standard linear algebra diagonalization problem. That problem here is nothing when we now look at the Green's function here. To obtain this Green's function here means essentially that we can solve the many-body problem. So if you have the Green's function, that's just another way of stating that you have solved exactly the many-body problem or the quantum mechanical problem here. So this problem here can be, from a computational point of view, as hard as actually solving this standard problem here. So what happens often in the literature is that we would have approximations to this Green's function. And typically, if you have the non-interacting Hamiltonian, like what you are studying now in project number 1, we are dealing with the harmonic oscillator, plane harmonic oscillator. So for the plane harmonic oscillator, we can actually calculate this one because we know the eigenvalues of the harmonic oscillator. We have analytical expression for that. So that means that we can actually calculate the Green's function. The problem then, when we have the harmonic oscillator eigenvalues, if we are thinking of this as a kind of transition probabilities, that means that since we then have the harmonic oscillator, it means that the probability of making the transition from X to Y is going to be the same as making the probability the transition from Y to X. And that means that when we take the Metropolis test with such a non-interacting case, the Metropolis test, which is a ratio between probabilities, the ratios between the probability of making a transition from X to Y is going to be the same as making the transition to Y to X. And that means that it's just going to give us 1 in the Metropolis ratio. And that means, again, that we won't gain anything if we were to use, let's say, the harmonic oscillator as a way to guide the jumping in space. So if you look at this equation here, just to conclude, you can then rewrite this equation here in terms of a delta function, because this is nothing but a g, and this is what leads to the differential equation for the Green's function. And this is going to be a delta of y minus x. And assuming is in the same way we would have for x, this will be given by g of y moving to x. And this is going to be given by delta of x minus y here. Now, these are equations, when the way they're written here, they yield a result in differential equations. And we can solve these differential equations. For instance, for the harmonic oscillator, we can actually find analytical solutions to that. But if we have interactions, there are very few cases where we can find analytical solutions. So this is basically the same thing which we did when we looked at the solution of the diffusion equation. So this is parallel to what we discussed last time, to the interpretation which we had before. So we had this for the probability of y of t plus delta t starting in a position x at the time t, and dt here equal to the diffusion term, or the diffusion constant, d of x of w, and then we have the same probability of y of t plus delta t given a position x and t. So we should put arrows since we are dealing with a multi-dimensional, and I'm going to put a d of x as a vector here if we are in more than one dimension. So this equation is something which we saw last time, and we could find that for just a standard diffusion equation, this probability distribution y of t plus delta t of x at the time t is something which for the standard diffusion equation can be written as a 4 pi of 4 pi times d, and then we have a delta t here, and then we have the exponential, and we have minus of y minus x squared, and this is divided by 4 d of delta t, and this has to have a factor, an exponential of 3, because if we are in 3 dimensions, we should actually put a d here just to indicate the dimension which we are in. If we're just in 1 dimension, this just reduces to d equal to 1, and then we don't need to have the vector signs. So this would be the solution to the case when we have no drift force, and that gives us a metropolis ratio of the transition probabilities, which is going to be equal to 1, and that means that we have a process which is reversible. So going from y to x is the same as going from x to y, and that will not help us in the importance sampling. And that's why we add this so-called quantum force, or this drift force, and that leads to the solution of the Fokker-Planck equations. So this was a kind of digression where I wanted to link what you have seen before with a quantum mechanical interpretation. Now, the problem with quantum mechanics, as it is with any type of problem here, is that if we want to find this Green's function, the exact one, which represents the transition probability, that means solving the full many-body problem. So making approximations with independent particle ansatses for the wave function, like we are doing now with the harmonic oscillator, would give us then a transition probability which is equivalent to the standard plane diffusion probability when we don't have a drift force. And that means that going from x to y has the same probability as going from y to x. And then we wouldn't gain anything. So the way you can view this importance sampling is us trying to find a way to guide the random walker using existing formalism. And what we've done here is simply to take a classical equation, which is the Fokker-Planck equation from transport theory, which again is a modification of the standard diffusion equation with a drift term, and then just use this machinery in a way to guide the random walker, but where now the probability is replaced by a quantum mechanical probability. So that's the kind of, if you wish to stay at this kind of overarching level, this is one way to read what importance sampling is about. Now, it's very easy to end up in lots of technicalities here. And that's why I have relegated a lot of the discussion to about the Fokker-Planck equations and the Langevin equation in the slides here. So if we get time, we can go through some of them. But I would like to spend a little bit more time on the technicalities which are relevant for us when it comes to coding. And I think that's the more hands-on and practical aspect, which is important for us when we are solving the project. So unless you have any questions, I would like to go back to the Jupyter notebook for this week and discuss with you some of the technicalities which you would have to plug in when you're writing the code and which you would have to think of. Now, keep in mind that the code we are setting up now in the beginning, we are leaving out the more complicated part of the wave function. That means that we're leaving out the correlated part of the wave function. And we are just looking at the wave function, the ansatz for that, as a product of single particle harmonic oscillator wave functions. And that's going to make the testing and the development of the machinery much easier. Now, in the code example, which you'll find in the slides, you will find a case where I've made just a small modification to our system. So it is a system with two particles in a harmonic oscillator trap. So it's very similar to what we have. But what I've done now is to add a correlated wave function. And let me just write this down so you have the technicalities on board. So let me just bring up the trial wave function, which I'm plugging in this example in the slides. So I just wanted to bring that up because that is a little bit different from what we are going to have in the project. So let me see now. I just got that one. Here we are. So if we now look at the trial wave function in examples, in code examples, and this is something which is tailored to a Hamiltonian for two particles, where we now have two particles moving in a harmonic oscillator potential and interacting with a repulsive Coulomb type interaction. So the Hamiltonian in this case is going to be the kinetic energy of the two particles. And now I'm putting h bar equal to 1. So h bar is equal to the mass of the particle, is equal to the electric charge, is equal to the permittivity in vacuum, and everything here equal. I just put all these physical constants to 1. So what I'm having now is the kinetic energy of particle 1. And then I have a similar one for the second particle, divided by 2. And then I have a harmonic oscillator potential, which is just now 1/2. And then I put all the physical constants equal to 1. And R1 squared plus 1/2 of R2 squared. And then there is a repulsive interaction, which I simply have scaled now to be given by the function which is inversely proportional to the relative distance between two particles. So this is a scaled Hamiltonian where I've gotten rid of all the physical constants. It means that it's a dimensionless Hamiltonian. And I would have to scale the final resulting energy with appropriate constants to get the right dimensionalities again. So my energy is going to be a dimensionless quantity. So the distance here is also dimensionless. This is the Hamiltonian. So what you are seeing in your case is actually something which does not have this term. So in our equations, we are dealing with, in the beginning now in the code development, we are basically just dealing with this type of Hamiltonian for 1, 2, and many particles, and 1, 2, and 3 dimensions. And the benefit then is that we know the analytical solution to the problem. What we are going to add later is an interaction, which is a model. In this case, in the examples in the slides, I'm using this term here. And this term here puts a minimal condition on the wave function. So I'm going to have a trial wave function, which is going to be given by a term e to the minus alpha squared. And then I'm going to have an R1 squared plus an R2 squared divided by 2 here. This is the kind of term which we are looking at now. But then, due to this interaction term, I'm going to put in a correlated piece, which I'm just going to call a function f. And this is going to be something which depends on the relative distance between two particles. So this R12 here is just a scalar, and it's given by R1 minus R2 here which obviously in 3 dimensions is nothing but x1 minus x2 squared plus y1 minus y2 squared. So I'm bringing up these terms because these are things we have to pay attention to when we now are thinking of encoding this in an efficient way. So I should say that the term which makes life difficult for us in the calculations is obviously the term which has to do with the correlations here. So this alpha is going to be a parameter. And then this term f here is also, I just forgot to put in, let me just rewrite this one. So this is a function R12, which depends on a parameter beta. And an ansatz for this term here, which allows us to cancel divergences in kinetic energy and potential energy when R1 minus R2 goes to 0. A typical term here is called a Padé-Jastrow factor, and it's given by an exponential, where I now have R1, 2 here as an argument, divided by 1 plus beta of R1, 2 here. So this function here, even the just having the numerator with a parameter beta is something which obeys an important feature. So when you look at the differential equation which you have here, this equation here, no, not the differential equation, but the differential operators, when you rewrite this in terms of the relative degrees of freedom, you would have for the 2 second derivatives for particle 1 and 2, you will get a term which is proportional to the first derivative of the wave function divided by 1 over the relative distance. Now, in order to cancel that divergency when the relative distance goes to 0, there is a similar term in the potential energy, which leads to a divergency. So if you have this shape here, then you're guaranteed to avoid these divergences, because then with that specific term, the 2 divergences will cancel when the relative distance goes to 0. So that's a minimal requirement of the wave function. Now, the example which you have in the slides then, in the code example here, is this function which you see here. So this one. So we have 2 variational parameters. So the set alpha here, which we wrote in terms of vectors, is given by a parameter alpha and a parameter beta. Then what we need to plug in then is the derivative, or actually the second derivative of the kinetic energy with that function. And this is where things start getting complicated, because we would ideally like to have an analytical equation for that, but sometimes this is not fully possible. And that's where we end up with numerical derivatives of the trial wave function. But let's go back to the code and let me show you how we can implement this. This was just a small digression. So what I have here is actually this wave function implemented in this function which you see here. So it takes the position of particle 1, particle 2, it receives this variational parameters, it sets up the relative distance, as you can see here. And in this case, I'm just looking at the system in 2 dimensions. So there is the component here 1 corresponds to the y direction, and a component 0, which you see here, corresponds to the x direction in a Cartesian coordinate system. Then I have this denominator, and then I calculate the final wave function. And here I have the analytical derivatives of that function. And this is something which we later will replace with automatic differentiation, because then we have much more flexibility in setting up the trial wave function. Because every time you now add a new term to the Hamiltonian or the new trial wave function, that's when you really have to go back and calculate new analytical derivatives. And with the local energy, which now contains these, so what you see here, simply the analytical expression for the local energy, I can calculate also the quantum force. So this would be the beginning of the code. And then in the Monte Carlo sampling, what I have now is a time step delta 0 delta t, which is used in the setup of the Langevin equation. I have a loop over the variational parameters of alpha and beta. So this runs over the number of variational parameters. I'm zeroing out the energy and the energy squared contributions to the expectation values. I'm setting up the initial positions as a function of number of particles, which are 2, the dimensions, which are 2 here, and then I'm using this normal distribution here with a 0 mean value and a variance which is set to 1, times the square root of this time step. And then I find the old wave function and the old quantum force by just calling these functions. And when I'm now looping over things here, I suggest now a new trial position where I use this Langevin equation to set it up. Then I calculate the new wave function, the new quantum force, and I use the quantum force to calculate this Green's function. But I'm now calculating the arguments as ratios between the denominator and the numerator. And then I calculate the exponential at the end. And then I have my new Green's function here, which is multiplied with a wave function u squared divided by the old wave function. And then I perform the metropolis test, which you see here. So this is nothing but the metropolis test, where I test this ratio in order to find the acceptance probability. And I test that ratio by simply, if it's accepted, if it's smaller than a given random number smaller than or equal to that probability, then I accept the move, the suggested move, and the old position becomes equal to the new, and the old quantum force becomes equal to the new one which I calculated. And then I update my delta E, the contribution to the energy, and then I calculate the contributions to the energy and the energy squared, and then finally calculate the final expectation values, which are then returned as a function of alpha values and beta values. And finally here, I will then plot these equations. So let me just quickly run through this, and then we can just call these functions here. And this is just going to run a little bit, and I'm going to reproduce this one after the break here. So I went a little bit over time. So the, let's see, I have a, okay, I need just to rerun this during the break here because I forgot to initialize this piece here. Okay, so after the break, we are going just to look at the results. And then I wanted to discuss some technicalities about the way we are going to encode the wave functions in the most efficient way. And this is something which becomes particularly important when we are looking at the correlated part of the wave function, when we have an interaction between the particles. When we simply have just a product of single particle wave functions, life is much, much simpler. So before the break, we started to look at the program for this example, which is just only a little bit different from what you're having in project number 1. And the difference here resides in the fact that I'm using the full interacting part of the Hamiltonian, which is here given by a repulsive Coulomb type of interaction or a repulsive type of interaction / potential, which depends on the relative distance between the particles. And this is what is being plugged in here, and where the local energy now contains a derivative of this trial wave function, which has the standard harmonic oscillator piece, which you see here, which then gives you this alpha times R1 plus R2, which is exactly what you are programming now for 1, 2, and many particles in 1, 2, and 3 dimensions. And then it contains this denominator here, which is a piece which contains information about the correlated part of the wave function. And what we have done here is to let us be guided by the physics of the system. And we require then that the divergency in the relative kinetic energy, there's a divergency from 2 and 3 dimensions and higher dimensions, which goes like 1 over the R which r is the relative distance between two particles. And then there is a divergence in the potential energy, which goes like 1 over r. And in order to cancel these two divergences, if you have a repulsive interaction, you get a plus here. If you have an attractive interaction, you get a minus sign here. This is also discussed in my lecture notes. Then you have a model for the trial wave function. And the thing is, now what happens is that the derivatives get more and more complicated. And that's where automatic differentiation will come in at a later stage as a way to circumvent us setting up all these analytical derivatives, which is not the most exciting thing we do, in particular when you have dependence on the relative distances. And here I'm setting up the local energy and the quantum force with analytical expressions. And then I do the Monte Carlo sampling. I have 100,000 here. And I just run through this code during the break here. And all the variational parameters, I'm not going to repeat everything. I have two particles, 2 dimensions, 10 variational parameters. So I'm running a brute force calculation with 100 parameters. And every parameter here has 100,000 Monte Carlo calculations, which means I have 100 times 100,000. This is not a very efficient way of performing the calculation, so I'm just producing a grid. Later, we are going to use gradient methods to find the optimal parameters from where we can actually run the big calculation. So the thing which you will see here is a typical plot where you find the minimum of the function. The exact value is 3.0, and we're actually hitting essentially the exact value for specific choice of variational parameters. And there are still some fluctuations here. The curve is not that smooth, and that's simply because we have very few Monte Carlo cycles. If I were to run this with more Monte Carlo cycles, then I could increase this to 1 million. You will see that the curve would be much smoother. However, that is also a calculation which is going to be a little bit more time consuming. But the thing which is important for us now, when we are setting up the ratio in the Monte Carlo calculations, there are several things we have to think of. So one is the acceptance ratio. And now I'm just setting the wave function, the new one divided by the old one. But actually this is the, we have to square this. But in principle, we can just set up the wave function u divided by the old one. And we have the new one body piece times the correlated piece. So as of now, you guys are just doing the piece here. Now, there's one thing I wanted to discuss with you before we move on, but let's just conclude a little bit here. So what we will need also is the derivative or the gradient of the wave function. And that is going to be given by these derivatives, which you see here. So when we are going to include a interaction between the particles, we need a model for the correlated wave functions. So OB stands for one body part, the single particle piece, which you're looking at now for the harmonic oscillator. So we will need to think a little bit carefully about these different terms. So we will need this one for the calculation of the quantum force, but we will also need this one, this second derivative, when we are calculating the kinetic energy in the local energy calculation. So we need then the kinetic energy piece for each particle, which is now essentially given where we have this operator, where we have the action of the second derivative on a given particle I for a many-body wave function. So we need to be careful with that calculation. So in my case here, these are electrons, but in our case in project 1, they are bosons. And then the wave function is actually a bit simpler. So when we look at this derivative and we have a correlated piece of the wave function, we need actually to have derivatives of the one-body piece, the second derivative of the correlated part, and then we have a nastier part here. So this is something I wanted to prepare you for before we actually start writing code elements. So I want you to keep these things in mind. So we need this term here. We are going to need the quantum force term, and we are going to need this term here in the metropolis ratio. Now, as a small digression here, there are ways by which we can perform the sampling. And one of the reasons why we typically move one particle at a time is that if we move one particle at a time, instead of having to calculate the full wave function when we've moved all particles, we can just reduce that to the calculation of a single particle wave function. So let me show that in the Jupyter notebook here, because that's going to not in the Jupyter notebook, but on a whiteboard. So we have three quantities which we need to think of in the calculations. And these quantities are: one is the metropolis ratio. And we want to calculate this in the most efficient way. So the metropolis ratio, let's just call this for R, is going to be given by the wave function in the new position. And now I'm skipping this trial. I'm just going to write this as an R new. And R here, uppercase R, represents the positions of all the particles. And then we have a psi, the trial wave function, or in the old position. So that's a quantity we need to think of. Then what we also have is that we need to have the quantum force. And the quantum force is a term which goes like 1 divided by the wave function times 2 here. And then we have the gradient of the wave function. And finally, we have the kinetic energy when we are updating the local energy. And this is, again, also one of the terms where we are going to waste a lot of CPU cycles. So in the kinetic energy, what we have then is a term which goes like minus delta I divided by 2. And this is acting on the wave function. And this is then multiplied, divided with the wave function here. So we have to calculate this specific quantity here. Now, there are two different strategies when you now look at the metropolis sampling and the way you perform the tests and calculate quantum forces and kinetic energy. So one, you can move all particles and then perform the metropolis test. So that means that this R, old, which is now given by the positions of all the particles, R1 old, R2 old, etc., up to all the particles which we have present, N old. We can move all of them so that we get an R new here. So we would simply have a loop over all the particles. So we have an R1 new, we have an R2 new, and then we have the final Rn new here. And then we can perform the metropolis test. Then perform metropolis test. For this test, calculate the quantum force plus kinetic energy. So this is, there's nothing wrong in doing that, but what we have to be careful with is the number of floating point operations we are willing to spend here. If we now look at the next possibility, that is to move one particle at a time. And then perform the metropolis test, and then do metropolis test, which means we calculate this ratio R and compute the kinetic energy in the local energy, and the quantum force. And compute F and the kinetic energy. I'll just write the kinetic energy with a K here. Now, there are reasons for why it can be advantageous to actually move one particle at a time. So if you look at the trial wave function, which we have now, trial wave function in project 1, before we have added the correlated part of the interaction. So the trial wave function is psi of t of, and I'm going to write it R1, R2, up to R of n. That is proportional to a product of single particle wave functions. And now I'm just writing this in a way like this. So this has a quantum number alpha 1 of R1, a phi alpha 2 of an R2 here, etc. So it's proportional to this product. We have to symmetrize it or anti-symmetrize it, but we can leave that out for now. And we can assume that these particles have specific quantum numbers in addition to position. So this is the trial wave function which we have. Now, if you now move one particle at a time, so then we have, if you look at the ratio then, suppose we have moved particle 1. So if we do that, then we will have an alpha of R1 nu. But then all the other ones, alpha 2, etc., are 2, they are in the old positions. So I'm just going to write this one up here, like that. And then we have a phi alpha 1, and then we have R1 old. And then we have phi alpha 2, R2 old, etc. So all the other ones are in the old positions. So that means that we can actually cancel out these ones, so their ratio is equal to 1. And the only thing we are left with then, in the case we just move particle 1, is a phi alpha 1 in R1 nu, and then phi alpha 1 of R1 old. And if you're thinking of the harmonic oscillator for our specific case, this is going to be equal to e to the minus 1/2 alpha squared, and then I have R1 nu squared minus R1 old, and this is also squared. So this is the quantity which I have to evaluate. Now, the kind of thing you have to think of now is whether this leads to less floating point operations than moving all the particles and then dividing by all the particles in the old positions. So you will see that later, this may not be so obvious now, but you may see later when you're calculating, let's say, quantum mechanical system with fermions, then we have a one-body part of the wave function, which is going to be given by so-called determinants or so-called Slater determinants. Then it becomes much more, efficient to move one particle at a time than to move all particles. So you can actually use properties of determinants, which will allow you then to simply look at the updates of one particle at a time. When you look now at the kinetic energies, if you just move one particle at a time, or if you look at the gradients which enter the quantum force, you will see that then the only thing we need to look at is the derivative of the particle which we are moving. And then all the other ones which haven't been moved, they will just stay there. And then they will divide out with the terms which you have in the denominator. So if you look at the quantum force here, or the kinetic energy, if you move one particle at a time, because we are typically going to take the derivative or the quantum force of a specific particle, will then just depend on one of the particles we are moving. And then all the other ones, which are not being moved or not being dealt with, they will just enter in a factor here, which will cancel out a similar factor which you have here. So that means that we end up calculating the derivatives of single particle wave functions, which are normally easier to calculate when it comes to the number of floating point operations. So whether you move all particles or you move one at a time depends a lot on the type of wave function you have. So the typical wave function you often have in atomic, molecular, solid state physics, nuclear physics, where you can make an approximation with a one body part times a correlated part of the wave function. This is often a wave function which gives you less floating point operations if you are moving one particle at a time. So I invite you to take a look at this and count the number of floating point operations which are needed to include in the calculations when you move one particle at a time, or if you move all particles at a time and perform the metropolis test then. So you can do both ways, but what happens is that when you have a many-body problem where you approximate the wave function with a product of single particle wave functions multiplied with a correlated part of the wave function, then it can be convenient to move one particle at a time. So if we stay with this moving one particle at a time and performing the metropolis test, let's now just go back to the slides and look at some of the formalism. So whether you use moving one or moving all depends very much on the type of wave function which you have. So let's go back to the efficient calculation of the wave function ratios which enter the metropolis test, and the quantum force and the kinetic energy. So much of the, the complications or the floating point expenditure, the number of cycles you're going to spend, is going to be to reside in the calculation of the kinetic energy. That is essentially the most difficult part of the calculations. So if you go back, you see now that for the gradient, you need this term. And you can actually use this gradient when you're now calculating the derivative, because you will have the gradient of one part times the gradient of the other. So you can actually reuse some of these terms, as you see here. And what you see also now is that some of these terms here, they cancel out. So if you look at the correlated part times the gradient of the one body part, the one body part is just a product of single particle wave functions, as you are doing now in project one in the beginning. So it's only at the end where we're going to bake in the correlated part. And that allows us also to make the tests in a much simpler way, because we know what we should get. The harmonic oscillator is something we know the analytical answer to. And what we need to pay attention to now is actually how we calculate these terms. So I should say the one body part is a walk in the park, because this is very easy to calculate, as you have seen from the calculations which I put up on the whiteboard. The thing which is more difficult is actually the correlated part. So that's where you have the root of all evil in these calculations. And this is essentially linked up with the way this correlated part is set up. So typically, you can write this as a product of all these correlation functions, as you did with a one body piece. And the general form which you will have is something like this. And this is a product of interactions or the correlated part between particles 1 and 2, or 1 and 3, 1 and 4, in general just I and J. And this is something which you can rewrite in this term here, and you can split it and store it. So you would actually, if you're just moving one particle at a time, you would then just act on the particle which is being moved here. So we have this relative distance, which is given in 3 dimensions like that, or in 2 dimensions like this. And in our particular case, we are going to have a form which looks like this. Now, when we are moving the particles, we also need to keep track of the relative distances of the particles. So whether we move one at a time, or we move all particles and then perform the metropolis test, we have to think of ways we store this relative distances. So if we are moving one particle at a time, suppose we move particle 1, it's only this part here which will be affected. If you're moving particle 2, it's again the interaction with 1, 2, and then we will have 2, 3, etc., etc. So you can actually store this in a way here because these are just symmetric. So R12 is the same as R21, so we don't need to store that. So we can just store the upper part of a matrix, and the below the lower triangular one can be put to 0. And we know that along the diagonals, we don't have a contribution because we don't have self-interactions. So that's simply 0. So these would be the elements which we would need to store when we now are running the calculations. And this applies also to the function g. So we need to store r, and we also have a pre-calculated g value here, which corresponds to the positions of the particles in the old position. So when we do the importance sampling, then one thing we have to think of is the ratio between the new and the old. So C here stands for the correlated wave function. And you can rewrite this now in terms of the new and the old position, which is the current one. And for a kind of Padé-Jastrow factor, this often, which is the standard form, where we have this exponential form, which you see here, this one. This is a very common form for these kind of wave functions. What we end up with then is just the exponential of this delta u, where delta u's here are just the function differences between the new and the old one. And then depending on which particle we are moving, it's either this equation which kicks in, or it can be this equation which kicks in. So whether with this k, which one of these, so it's just running over the different particles which we have. So k is the one where we are, is the particle which we're moving. So we would then need to look at k here, and then we have the contributions from up to k minus 1 and from k plus 1. So in order to do this, so these are just hints and advices on how to set up the correlated part of the wave function. So in the beginning now, we are not that much interested in the correlated part, but that comes in a little bit later, because first we want to develop the machinery just for the harmonic oscillator. So this is what you see here is something which becomes important at a later stage. Then, when you're setting up things, so some of this is not the most exciting thing we're doing, but take a look at these slides here, because they contain some general guidance lines about how to calculate efficiently these different ratios. So when we are calculating the quantum force, we would need to set up something like this. And this is going to run over all the particles at the end. And every such contribution here, when we look at a specific derivative with respect to particle k, is something which is now going to contain a loop up to k minus 1 and from k plus 1 to the final number here. So for the quantum force, this is something which we need to set up. And these, both of these expressions here, they scale as n floating point operations. Now, there's another important aspect which I want you to think of, is that these correlated part of the wave functions, they have some symmetries which we can use. So that means that if you look at the expression which you have up here, due to this feature which you see here, this can actually be rewritten in terms of, instead of having a plus here, we actually have a minus. And then we have a gki and xj here. And this is something which we can then, if for the exponential case, depending on the type of function we have, this can actually be rewritten as a function which you see here. And then when you're now setting the derivatives up, we actually end up with a term where we, since these are relative distances, or relative, it's actually the absolute value, the functions depend on the absolute value. What we end up with is an expression like this, where this Rij is the absolute value, whereas this xj minus xi are going to translate into vectors. So what we arrive at then is something which looks like this expression here, where these are now vectors. And remember now that the gradient is actually a vector. And then we have to sum over all the values of k when we have many particles at play. So these are just the individual derivatives. And remember now that you have a sum over k here. So I invite you just to go through these derivations, because you need to think of that when you're structuring your program. And we can set this correlation factor, which often is given in terms of something called a Padé-Jastrow factor, like the one we saw for the 2 electrons. And that's typically going to be an exponential with a given function as an argument. And that means that when we take the derivatives, we can simply plug in this ansatz for the trial wave function, for the correlated part of the wave function, which then transforms into this equation, which you see here. And that's something which has to be coded. And that will, the final result will obviously depend on the way we have defined this function here. Okay, so then we have the next part, and I'm setting it up here. This is the second derivative, and that's also something which I invite you to look at. Later, we are going to replace these functions with automatic differentiation, and that's going to make life much, much easier when it comes to finding the analytical derivatives. However, there are considerations which are important to think of. And at the end, the type of derivatives which you need to code in, depending on the form. So if you have this standard form, which has an exponential of a function f, you will end up with a function which looks like this, which has to be coded. So I invite you to take a look at that. In the slides here, I've put in additional information about the Fokker-Planck and the Langevin equations, but I will not go through that in the lectures, because I wanted to now to point to the next topic, which is going to keep us busy in the coming 2 weeks. And this deals with the optimization problem. And the reason for why I'm not going to go through many of these technicalities is that these are topics which many of you may not have seen before. And I leave this as a kind of material you can take a look at yourself. There is a textbook which I referred to last week, which has a lot of these derivations. But if you're not too familiar with transport theory and the statistical mechanics of transport theories, then this is something which you could just treat as an ingredient in finding a way to simulate the movement of the particles by using a result from classical transport theory, but where the probability now is being replaced by a quantum mechanical probability. So I hope you can forgive me for not going into all these details. That would sidetrack us from the essential component of what we are doing now with project number 1, where we are trying to build up a more professional Monte Carlo code. So what I wanted to move over to now is the optimization part. And I'm going to switch over to the whiteboard again. And I wanted to bring up what we are going to spend time on in the next 2 to 3 weeks. So let me just now bring this up here. Now I don't understand why my whiteboard turned black here. Okay, so let me just see why my whiteboard, I don't know why my whiteboard just turned black. Maybe it doesn't want to show these things. So let me try again. Here we are. I just needed to reset it. Some black magic in technology. So if we look at what we have now, there are some basic elements of a Monte Carlo code. Of a VMC code. So what we have seen is the metropolis sampling and the Markov chain. Metropolis plus the theory of Markov chains. These are the basic algorithmic elements. And then we have another thing. We have the expressions for the local energy, or EL, as a function of all the positions and quantum numbers of the particles and the variational parameters. We have an expression for the trial wave function. And we have the probability, so which is now a P of T here, which is proportional to the trial wave function squared. And I'm skipping the R and the alpha dependencies here. We have also added to this theory, we have added importance sampling, which leads to what's normally called the Metropolis-Hastings algorithm. So often when we think of the Metropolis algorithm, we tend to relate that one to what's normally called a brute force sampling, where we don't have a transition probability for modeling the transition from a position X to position Y. So this leads normally to what we call the Metropolis-Hastings sampling rule. And then we have baked in a model where we have random walkers, which now are spanning space. And these random walkers, they are now moving according to a specific distribution. So we have plugged in more physics information in the way the random walkers are moving, compared to the standard Metropolis choice, where we assume that moving from X to Y, the probability for that, and moving from Y to X, they have the same expression. And that means that in the ratio, they just give us 1. Now, the next part, which we need, so in the importance sampling, we have defined this quantum force, which is given by 2 divided by the trial wave function times the gradient. So these are the basic elements which we have been dealing with till now, and we have looked at the simplified trial wave functions where we still leave out the correlated part for the wave function. And this is simply done because that allows us to test the harmonic oscillator and test all the machinery with a simple case where we know the exact answer. But now comes the next piece, and that is one of the more important pieces, and that's the optimization part. So this is going to give us a way to find the optimal parameters with the fewer cycles, so that we can actually start mounting the big calculation where we have the minimum of the energy or the best possible expectation value for a specific variable. So what we are doing now is to calculate the expectation value, so this E of the local energy, as a function of these parameters alpha. So this is what we normally have written out now as an integral over R element in the domain of all possible events. So we have a D of R, and then we have this probability of R as a function of alpha, and multiplied with the local energy, which is a function of R and these parameters alpha. So we're going to put a vector here because we can have many parameters. So this expectation value is typically something which we till now, and you saw that in the implementation in the code here, is something, if we now think of a one-dimensional variable alpha, so we have just one variable alpha, and we look at this expectation value of the local energy of alpha, the typical quantity which we would have now would be something which looks like this. The energy is a convex function as a function of alpha. And here we would have what's normally called the alpha optimal. And we have performed calculations for an array of values. So we will typically start with 1. And all these values here, they may have a standard deviation. So let me just point to the values here. And there may be a standard deviation. So let's mark that with red here. So we can have a standard deviation. Often what happens is that the standard deviation becomes smaller when we're getting close to the minimum, and then it gets larger typically when we move away from the minimum, etc. So this is a type of calculation here, and each calculation, each point has the same number of Monte Carlo cycles, is obtained with the same amount of Monte Carlo cycles. Amount of Monte Carlo cycles, or Monte Carlo runs, or whatever we might call them. I normally call them cycles. And a cycle is us running through all the particles and moving all particles and then updating the energies. Now, when you look at these calculations here, so what we actually, what we want now is the following. So we want this alpha optimal, which I'm going to write as an alpha hat here. And that is going to be the argmin for all the alpha values which we have. So alpha is now member of real values with m possible parameters. And we are going to optimize the expectation value. So for those of you familiar with machine learning, this is something you have seen many, many times before, where we typically optimize something which we call a cost function. So I'm anticipating some of the things which will come in connection with project number 2. For those of you interested in applying neural networks to this type of systems, this is something which then mimics very much to what you have seen before. And then we're going to let the trial wave function be represented by neural networks. So this is one of the possible paths for project number 2. But what you see here, this equation here, this is essentially what we are going to try to solve. However, what we would like to now is to avoid to calculate every single point here with the same number of Monte Carlo cycles. So what we would rather like to do is actually to perform the calculations of each of these points here with fewer cycles. So suppose we have a final run here, which runs with 10 million Monte Carlo cycles, but that we could find this alpha parameter with just fewer Monte Carlo cycles, let's say 10,000 or 100,000, which would be a cheaper calculation. And then when we find the optimal parameters, that's when we start the big calculation. So the question is now, can we optimize the search for this alpha optimal with less Monte Carlo cycles? So this is the kind of questions we want to address. And this is why we are going to look at various optimization methods like a gradient descent method and so on. So the question which we have now is, can we optimize these calculations, optimize the search for this parameter alpha opt, this alpha hat here, which is the same as the alpha optimal, with less Monte Carlo cycles. But since I asked the questions, it means that I must have an answer to it. And the answer is obviously yes. And this is what we're going to deal with now, and how to actually perform these calculations. So what we will need is, so the answer is yes. And this leads to gradient methods, where we're actually going to start with an initial guess for these parameters alpha. And then we are using a gradient optimization to find the best possible parameters. And when we have the best possible parameters, that is when we are going to launch the big calculations. So this leads to gradient methods. And we are going to look at the following things. So we are going to look at the plane gradient descent, which many of you have encountered. And the harmonic oscillator is actually a gentle case. It's a gentle case because we have analytical expressions for the derivatives of the local energy as a function of the parameter alpha, the expectation value of the local energy. That means that when we are now implementing these methods, we have a test bed, which allows us to practically benchmark these methods against exact results. So this leads to things like a stochastic gradient descent, which many of you have met before. Stochastic gradient descent with and without momentum. We are going to look at something which is called stochastic reconfiguration, which is another technique, reconfig, which many of you may not have met before. And after we've done that, we are going to, so when we've gone through this, so we have other methods, which are also called, some of you have met them before. One is the steepest descent. We have conjugate gradient descent, conjugate gradients. So these are famous methods. Now, all these methods, which you see here, these methods like these, they require that we can calculate the second derivative of the local energy, the expectation value of the local energy. Now, remember now that the expectation value, which we are calculating, this quantity here, is an expectation value, which we are calculating with Monte Carlo methods. So to calculate the derivative of this one with respect to alpha is going to translate into integrals, which we have to evaluate. These integrals are evaluated stochastically. So that gives a source of errors. And to calculate the second derivative of this quantity here is going to give us 6, 7 integrals to evaluate. And that means that this is going to involve too many cycles for this to be of interest. So that means that these methods like steepest descent and conjugate gradient methods, they are less used because they actually require us being able to evaluate the second derivative of a quantum mechanical expectation value. And that's an ugly beast. However, next week, we are now going to look at the technicalities here. And when we have these calculations, the other element which we need to plug in are statistical resampling methods. And finally, after that, we're going to include also parallelization. And with these additional ingredients, the gradient methods to find the optimal parameters. Then when we have calculated the expectation values, we are going to use resampling techniques to estimate the errors correctly. And finally, we are going to include parallelization. And that will be the final 3 elements which we need in order to have what we are going to call a professional Monte Carlo calculation. So the codes you're going to develop are essentially what you would find in the scientific literature and the way people actually deal with these problems. Okay, so this is what is going to come. So next week and the week thereafter, we're going to spend time on optimization in order to find the best possible parameters and then start our big Monte Carlo machine. So this stops today's lecture.